Good day, ladies and gentlemen. You're most welcome to this week's CNPS technical session. Now, we're unfortunately having some internet problems at the moment, which I hope we can clear up in the next few minutes with the speaker. But we'll just leave that for a few moments, and I'll address the topic and introduce the speaker presently. It will be a bit of a departure again, a welcome departure maybe, from our sometimes over tedious analysis of special relativity, which has to be done, and it's my interest as well. But it's nice to have a more general topic that we're hoping to have today. But before coming to that, if you'll permit me, I'll spend a moment or two just promulgating this video, which has been pre-recorded by our president, David de Hilster, in regard to the funding endeavor, which is now underway. Basically, the funding for running of our sessions and the whole CNPS organization is not totally covered by membership dues. It's partially covered thereby, and it's required to obtain some supplementary funding. One of the big holes actually in our funding is the payment for the server that we're using for these meetings. So I'll just play this pre-recorded interview or announcement rather, and I'll then come back to you. It only takes a minute or two. Right.
Hello, my name is David de Hilster, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Oh, all right. Thanks for your indulgence and patience in that. So this is one of the sessions which is hosted by myself, Ian Cowan. So I forgot to introduce myself. But we're having some difficulties with the speaker now. So I'm going to need your indulgence for a little while. Let me tell you what we propose anyway, or we had proposed to speak about. So John Hodge, based in the United States, has what he terms a scalar theory of everything, sometimes abbreviated to STOE, which he adverts to uniting the big, small, and the four forces. GUT was that general universal theory, I think, by extending Newton's model. Excuse me. So it's based on a classical system. And John reminds us that Newton established a major physics advance, which was confirmed by predicting the late return of Halley's comet. Newton identified three characteristics of bodies that have been identified as three characteristics of mass. Physics theory, restarting from Newton's speculations, and then describing the experiments of the 19th and 20th centuries, results in a model of the big, the small, and the four forces, GUT, which he calls the Scalar Theory of Everything, STOE. Now, okay. So I must just repeat that John has been in contact with me for some time, and I think the StreamYard or his own internet connection is quite inadmissible, and we're not able to go ahead on that basis. So what I've asked him to do, I've asked him to send me his visual aids by email, which he says he's just done. So I'm going to see, can I retrieve those? Let me see now what he sent me. Yeah, okay. Okay, he has YouTube links to them. So, okay, I'll deal with that in a second now. I just want to post the actual URL for this talk to the chat, because some people, if they don't have a direct link, their system brings them to the previous session, which is now expired. So let me just do that. Here it is. So I'll post it now. Okay. Okay, let me just see now. Yeah, we have comments, from Toby Grotz, for example, that Zoom would be much easier. But I'm not sure if it's you can try to start a live YouTube session and I can share that to StreamYard. Well, Franklin, John has sent me links. So let me see, can I open those links? There are two YouTube videos. Now, here's the first one. Okay. The first one is about 40 minutes, but I'm going to have to share my screen to get it working. So let me see, can I do that? Present. Maybe share screen would be the safest, I think. Share. Okay. Let's see now. Franklin, I'm just going to bring you up, maybe for your kind assistance. Am I going about it the right way? I've shared my screen, and I'm going to start this video.
Just go ahead and, well, hopefully you've shared the screen and you've shared the audio. So go ahead and try and play it. Let's see if we can hear it.
Okay, I'll keep you up just while I start it, because I'm not sure if I've played the audio. Let me see. How do I start it now?
Yeah, press the play button in the lower left-hand corner there.
Yeah, it doesn't seem to be operative. Maybe I have to bring it up. No, it's not operative there.
You can't press the play button?
No.
Well, if you put the link for the video in the chat, I can play it.
Oh, okay, I might do that. You're probably more adept at these things. So I've got two videos. I'll put the two of them in the chat now. Let me just retrieve them.
Yeah, and the previous link you have there for StreamYard, that's for the green room. So if
Jim Keane can never get in, so he's asked me to post that. I do that now.
Yeah, we frequently have this problem where it doesn't take you to the right session.
Yeah, I don't have a problem. I don't know if that's because I have admin facilities.
Well, as moderators, we just go into StreamYard.com and click on the session. The other people coming in through that natural philosophy link are getting like last week's session.
Yes, that is true.
I think David said there's something else you have to update so that generic link works.
Oh, okay.
That may not be happening. I'd like to figure out what that is.
No, it's not happening for him. He said he's deleted his history, and it's still. Okay, I've just sent you that.
Yeah, did you just put that in the chat?
No, I didn't. I sent you the email. I forwarded it to you.
Oh, you sent me an email? Okay. Well, let me check my email. All right, let's get these videos going here.
Okay, let me get back to the main screen now.
And put that video in. Yeah, I also have a paid YouTube account, so you won't have to suffer through any commercials. Okay, so I'm going to go ahead and share screen.
So I'm not sure if sharing videos or sharing the screen is best.
Okay, no, that's not the one. I want to share the other window here. Share screen. That one. Okay, there we go. We've got that one.
This video is an introduction to the scalar theory of.
So can you hear that?
Yes.
Okay, then we're good.
If I remove us.
Everything. The STOE. The STOE is a Kuhnian type of paradigm shift. That is to say, it's accurate, it is empirically agreeable with observation, it is consistent, it's internally consistent and externally consistent with other successful theories. That is to say, it corresponds to general relativity and quantum mechanics. It has a broad scope. It explains general relativity, quantum mechanics does, and it explains some of their problem observations. The STOE is simpler, Occam's razor, and it is fruitful. It suggests new phenomena or new relationships between phenomena, and it has made some predictions which are later found. Rival paradigms are incommensurable. So the Big Bang kind of models are not be too helpful here in thinking about or understanding. The STOE fundamental postulates are that it accepts a fractal universe, that is, a self-similar, so we can take observations in our size scale and at least the equations of those observations and apply them to the kind of things that are in the smaller and larger size scales. It accepts the spherical principle. That is to say, forces are going to be inverse square proportional to the radius, which is the surface area of a spherical area beyond the source, and the potentials are proportional to the inverse radius. The two constituents of the universe from ancient times, people have seen that there were discrete things like trees and rocks, and then there are continuous things such as water. In the STOE, the discrete things are called Hodge, and the continuous stuff is called a plenum, which is kind of like an ether. And I use the term plenum, which follows Descartes, to distinguish it from other types of ethers. And the problem the STOE then has is to determine what the characteristics of these two things are. Now, the STOE starts with experiments and observations data. That is to say, it looks at the data rather than what other people think of the data. For example, when you look at the redshift of galaxies, normally a lot of people refer to that as a Doppelshift, but a Doppelshift is a model of the redshift, you see, and that assumes a model. So we don't do that. We look at the data. In the Michelson-Morley experiment, people assume that it doesn't show the luminiferous effort. Well, that's true, it doesn't. But then we have a plenum. And what the data does show is that there is an effect that they found. It's smaller than what they wanted, and it's in the wrong direction from their viewpoint. So we start with the raw data. The universe is basically cause and effect physics. But where the cause effect is unclear, the math can use correlations among data points to help develop the cause effect. We see these correlations and the probabilities and that kind of thing being used in quantum mechanics, but all that means is we don't understand what the cause and effect is at those scales. Bodies, that is to say hot assemblies, have 3 dimensions and have a position and velocity relative to other bodies. Time in the STOE is only now. No past, no future. There is only now, and it's called the streaming now. We note that physics postulates are generally time symmetric, but what I want to do is develop cause effect, so it's cause and effect in the next now. I start with Newton, and Newton has 2 books, the Principia, which everybody seems to know, and Optics, which in the 1690s and so, Newton didn't know what gravity was, and he said so. In Optics, which started in around the 1700, and I used the 1730 edition, he started to rethink that, and he actually did, in my opinion, come up with a bunch of speculations about what was going on, that is to say, about gravity. In the Principia, Newton identifies 3 types of mass characteristics or body characteristics: weight, inertial mass, and gravitational mass. You'll note this is different than what the modern theories, they talk about one type of mass. So the Lagrangian and the Hamiltonians talk about one type of mass, and then they try to lump all this in there, which to me is a source of several problems that the modern theories have. What the STOE does is it measures position and velocity of fallen bodies. Remember, that's what we said. Then what Newton does is he mathematically transforms it to a mathematical symbol, which is he calls force, in this case, the inertial force, which is not measured. It's transformed quantity calculation through something he calls a proportionality constant, which is inertial mass. Then he transforms gravitational mass to another type of force, the gravitational force, which then he treats like a continuous substance and its effect on a falling body, which is the gradient of the plenum. Then you set the F's equal and do the calculations, and everything else is well known. In his book, Optics, and again, this is where he's going to be developing a speculations about what gravity is. So he expanded on how the gravitational mass may be impressed on another body through the weight in relation to gravity and light, stated in modern terms. The bodies is query 1 in optics. Bodies bend passing light around an amount inverse to its distance. Light passing close to edges are diffracted in fringes. This is the beginning of the small world, that is to say, interference. Light path begins to bend before reaching a body or a slit. Now, this is a little different than what most people today tend to think. But Young, in his experiments later on, also thought he saw light beginning to bend before it actually reaches a body or a slit. And that is not accounted for in current theories, because in interference experiments, the light has to pass through the slit before it bends. Black bodies absorb all light. Black body radiation is kind of understood. Sun and stars are black body radiators, of course. Light is corpuscles, particles, Newton speculates. And they are pushed around, which is the divergence of the ether's density, by waves in the ether that overtake the rays of light. Overtake means the waves are traveling faster than light. It's not a big stretch to say much faster than light, which the STOE does. That is, say, gravity is not force. Gravity is the effect of the divergence of the ether. Also, like a rock thrown into water, you note this is two things. It's the rock and the water. It's the corpuscle and the wave that's what give you interference. A medium that refracts and reflects light also allows light to heat bodies. Sure. Refraction of light implies different densities in the medium. Increasing ether density causes light refraction. Yeah, that's just 21. Rarer ether is within dense bodies, such as Earth, and increases with distance, thereby causing gravity of those great bodies. Everybody is endeavoring to go from the denser parts of the ether to the rarer. That's the attraction of gravity. Newton was suggesting a reductionism step by positing an ether whose divergence exerted a force, weight, that caused gravity, that caused the diffraction, reflection, and refraction of light. Corpuscles as light and as components of matter. That is to say, support for the ether and corpuscles was because the model could explain several diverse observations, then known but mysterious, rather than by direct observation. Newton was speculating about a theory of everything, period. The next step in the STOE was the quasi-steady state cosmology. This model, which came about in the 1990s through the early 2000s, added that the stuff of our universe continually enters through sources at the center of galaxies. It added a creation term to the right side of the general field equations. Now, you'll note this is a lot different than Big Bang, which had everything created all at once. This model accounted for rotation curves, which the Big Bang model needs dark matter, and other unexplained general relativity observations. That's its advantage. This is a book. Narcolar is still pursuing this, so you can look them up on archive and see some of the papers. Note we're dealing here with forces, not energy. This is Newton's model of forces. The action-reaction is that bodies cause plenum changes, that is to say the gravitational mass of bodies cause plenum changes, and the plenum directs the Hodge. This is the universal equation. This part is the rho density, which is the plenum density, at some point in space. This part is from source galaxies, otherwise known as spiral galaxies. This part is from the sync galaxies, which are elliptical galaxies, and this part is from all Hodge in the universe. This quantity and this quantity are source and sync strength of the galaxy sources and sinks. I use the B-band luminosity, but more about that later on. This is essentially the gravitational mass of each Hodge, which is yet to be calculated. After calculating the rho density at a point, we then take the gradient of the rho and apply it to the normal of the surface of a Hodge to determine the force on that Hodge. And then that force is going to direct the Hodge, and of course, later on, all bodies in motion. You will note that this equation is Machian, which general relativity is not. And as far as I know, this is the only really Machian thing that's going to use. It is causative in that the sources, the sinks, and all the matter in the universe cause the plenum density at some point, which then exerts forces. The application of the spherical principle here has 3 and only 3 spatial dimensions. This force is the only force and is going to be magnetic, and we're going to get into that here in a little bit. Therefore, the speed of the force determines the time characteristics. The speed of change in the plenum waves, is much greater than the speed of light. Van Flandern measured this relative to the sun. Stefanovic looked at it from the speed of Coulomb forces. And these are 2 video on YouTube that are very interesting, determining speed of the entanglement in quantum mechanics. The speed of Hodge is this maximum speed, is the speed of light. And that is according to the Lorentz-Ether theory. Now, this is the maximum speed of anybody, is only the speed of the Hodge or the photons. It is dependent on rho, and because it's dependent on the plenum density, it can change. That is to say, we're looking at a variable speed of light theory here. All interactions are Hodge causes waves in the plenum waves propagate faster than the speed of light, and then the plenum gradient on the Hodge surface directs the bodies. This is Newton's weight, as we see. Therefore, all interactions are, to put it in the phrase of Bell's inequality, all interactions are non-local. We're going to start by looking at the small. The key to understanding the small for a particle model, a photon model, is diffraction and interference. One of the huge problems that we have to overcome in looking at interference is coherence. Coherence is a huge problem for particle models. What exactly is coherence for particles? Young's experiment was accepted and interpreted because it suggested wave-like behavior, because it seemed the only explanation of coherence, which was shown in diffraction and interference experiments. We know that the Afsar experiment rejects Copenhagen interpretation, which is wave-particle duality, and some other interpretations in quantum mechanics. The STOE explains how coherence occurs for particles, and that is a big thing that particle models had to overcome. Soon we'll be talking about a transparent mass experiment, which rejects all models of light, except for the STOE. What is a Hodge? In the STOE, we have found that the STOE is a magnet whose plenum evolves to gravity. And we're going to see that. This model came about in conversations with Andre and Emmanuel here. At the time of those conversations, they were looking for monopolar magnets. Emmanuel likes spherical magnets. I like flat magnets or disk magnets because they can form structures. Andre developed an experiment where he was looking at repulsive effects of magnets. And as far as I know, nobody else had done this before, but Andre had a issue. And his issue was that he measured only a very narrow range. So I built a different apparatus here to measure repulsive strength of magnets. You see that here's an upper magnet and a lower magnet. And this lower magnet is attached to a weight scale. And what we're going to measure here is the repulsive force that the upper magnet causes on the lower magnet. There are 5 papers that I looked into this. Andre's data was in what I call zone 3, which is in this zone here. Now, the force varies in this range approximately as 1 over the distance cubed, which Andre determined. The problem was that this is also well fit by an exponential equation, and the data cannot decide between the two. I looked at data that was much further. In the zone 1s there, the force varies as 1 over the distance. In zone 2, the force varied as 1 over distance squared. Paper 5, and where we're looking at is right in there. That is the asymmetry, which, as we'll see later on, we're going to propose evolves into gravity. The following video is a quick little demonstration of what we're talking about here. Here we have a glass tube with a wood dowel inside. And these are magnets, very strong magnets. I've colored the North Pole black and the South Pole red so that you can see it. Now I'm going to insert this into the tube. So I insert these into the tube. The tube is slightly larger than a magnet so that they'll stay nearly axial. And let me see, we're looking at the North Pole first. So as you can see, the North Poles repel each other. Now let's mark North Pole repelling distance by the white paper strips. Now we're going to reverse the poles. Now you can see that the South Poles are closer together with the same weight on the top, and they're slightly closer together by approximately the width of one of the magnets. Therefore, the repulsive strength of the North Pole is slightly asymmetric to the South Pole. No, electromagnets do not show asymmetry. This then is a HOD. High level row to low level row, these are the force lines. One side is stronger than the other. And so one side has force lines which do not terminate on the other side. And this is what evolves to gravity for distances greater than the atomic scale. You'll know then that Newton's force law for gravity is simply an approximation of what's really going on at the small scale. The STOE has noted an inconsistency between Faraday's law of induction and Ampere's circuit law. That is, there are 2 different types of magnetic field, and that is explored in the paper that you see there. Faraday's law of induction is that a permanent magnetic field moving produces an electric field in a conductor. A changing current in an electric field produces an electric magnetic field. This is the bios of our law. You'll note that a cross product of the current introduces a magnetic field at some point. That is to say, the current along the entire length of the wire produces that current. That is what we're going to explore with an experiment.
Here I have 2 disc magnets. If you'll note that if both sides north is up, they repel. If one is north and the other is south, they attract. We're going to use this to detect current in the wire and the resulting magnetic field. Here is this magnet. I've attached it to a piece of wood and mounted it on a weight scale. Now there's a small gap of about 0.5 millimeter here, and we've attached 2 wires that's going to provide current. Here then is a multimeter. I turn it to the resistance range, and you see it's measuring about 0.4 of an ohm through this current path. Let's change back to voltage. Here is the battery. And what I'm going to do is attach the terminals to the battery. Now, this is not, there's some problems here. When I attach the terminals, the battery is going to provide a lot of current. It's going to actually discharge the battery faster than it should, and therefore things are going to get hot, and the battery's not going to last too long, and the current level is going to be varying. So we need to be quick about this and not take too much time in the actual measurement. I'll attach one terminal. I'm going to turn on the scale, the weight scale. It's reading 0 because it's zeroed with that weight on there. So let me attach the battery. You see that we're measuring a voltage, which means the current is flowing. And this is reading 0.36. The next experiment is to move the electrodes here very close to the magnet. Now we're measuring 0.39, which is very close to what we had in the full length of the magnet. That means the current and the magnetic field produced in this part and this part are having no effect on the magnet here. It's only the current over the magnet. To see this, let's do one more little test. Here, all the current is going to be on one side through the brass bar here and not over the magnet. We're getting a voltage reading, we're getting current, and the reading here is 0. That is to say, there's current flowing here, but there's no magnetic force being exerted on that magnet. This means the Biot-Savart law is rejected.
The experiment indicates the magnetic effect is ejected from the wire perpendicular to the wire, but not at any other angle. This is also experienced in radio signal antennas. The STOE suggests the Hodge have a magnetic field and travel at the speed of light compared to the plenum wave, which travels at many times the speed of light. This is a diagram depicting another experiment we're going to do. We have a coil of wire that surrounds then a magnet, which is in the middle. In the STOE model, only current from perpendicular to the wire will have an effect as depicted in the C2 areas with delta equal to 1. In the other areas, perpendicular to the wire does not overlap the magnet. Magnets on a scale, and I'm going to measure the force that is exerted on the magnets by the coil of wire. This is the coil of wire with a power supply that's going to provide about 1 amp of current. We place the magnet in the coil and measure the force that when the current flows. In the center, here as you see, and later on at various radii here near the edge of the coil. This is a plot of the result where the force at some radius is compared to the center force, and the bottom line is both the data and the STOE line plotted, and the upper line is what the Biot-Savart law says it should be. You can see that the actual result agrees with the STOE and not with the Biot-Savart law. Faraday's law concerns moving magnets. So we're going to drop a magnet through the coil with a voltmeter attached. The voltage measured from the center drop to an edge drop is the same. This suggests that a magnetic field induction is dissimilar to the electric field characteristics in the Biot-Savart law. Maxwell's equations should be redone and should include causality. Photon diffraction is a central mystery of subatomic particles. Some observations of light suggest a particle model of light, such as the photoelectric effect. Other models suggest wave model, such as interference and diffraction. To have a better model of light, we need one of two types of models. One, either create a wave model of the particle experiments or create a particle model of the wave experiments. And that's what we're going to do. We're going to create a particle model of interference. The challenge of uniting the Newtonian and quantum worlds is to develop laws of motion of photons that obtain the diffraction experimental observations. Young's experiment, of course, was taken to indicate light was a wave primarily because it was a way to model coherence, and that seemed to be what was required for diffraction. The light that passes through a slit is allowed to impinge on a second mask in Young's experiment, and that produces the interference pattern. Coherent light is, by definition, light that produces a diffraction pattern on a screen after passing through a slit or a pinhole. Coherence, as far as we know, is obtained by either a pinhole in the first mask, such as in Young's experiment, or by light traveling a long distance, such as from a star, as seen in the Airy telescope pattern images, or from a laser. The model of a photon started with Democritus. He talked about corpuscles, that was the Newtonian term. But light has many different colors or energy levels. Therefore, photons cannot be a single type of particle. That is, the STOE photon is an emergent entity of Hodge, which are the corpuscles, and plenum, which is an ether. The number of Hodge in a photon determines its energy. The photon model in the STOE is a column of Hodge, and since photon monopoles have not been observed, therefore there are only magnetic dipoles. So we take a Hodge, a magnetic dipole, and a 2D particle, which composes all of the bodies, and therefore Hodge is a magnet. And we form them into a column, which you see here. And the plenum impinges on the surface in this direction, but then from the other direction, this way, there is no surface area, which means the Hodge is going to travel in that direction and travel with the fastest speed possible because there's no surface area here. As it travels, it's going to emit waves, like here, forward and backward. Emitting waves forward is then going to sense what is ahead of the photon and reflect those back. Remember, these waves are traveling much, much faster than the speed of light, than the speed of the Hodge. And therefore, we don't need retrocausality, which is one of the quantum interpretations. It's simply not needed because these waves detect it and reflects back. So here's an analogy that I use simply as a way so we can see things. I take these disc magnets you see here and simply line them up. They kind of fit together into a column. And of course, you'll notice that this is the direction of movement. A neutrino then is an assembly of photons, which you see here. You'll also notice that the direction out of the paper has no surface area here, so neutrinos can travel at the speed of light. This then is an electron, which is another assembly, not only of photons, But of neutrinos, you'll note that this kind of a structure here looks like a neutrino. You'll note that this structure has 4 different magnetic poles coming out of each corner. It's these 4 different poles that are going to give the result of the Stern-Gerlach experiment. Instead of spin, it's this magnetic function, not spin. And of course, you'll note that if it travels in this direction, these are surface areas. And so the electron has surface areas in all 3 directions. So it is not going to travel at the speed of light, but is going to travel with a given orientation to minimize the surface area. And here's some papers that discuss this. Another interpretation of light is the Bohm interpretation. And its problem is, where does the pilot wave come from? The diffraction pattern minimum and maximum are at different locations for different photon energies. This is a spectrographic effect. And therefore, a photon must be the source of the plenum wave, which is the STOE interpretation. Here's some videos which are quite important here because they're going to demonstrate this single photon stuff really has to be taken with a grain of salt. The STOE, or I, in around 2012, developed a toy computer simulation model using the various assumptions of what a photon and ether is doing. So the first step for a particle model is to explain coherence in terms of particle action, which is what the computer simulation did. If you remember the structure of the photon, if you take each and every one of those Hodge is producing a pattern, a wave pattern in the plenum, and then apply the equations that are well known for dipole antennas, and you get then this kind of an intensity pattern of waves directly ahead and off to the side. They have minima and maxima. Now, remember these little individual numbers here. So I start with photons in the simulation, positioned randomly and traveling in the same direction. Like the Bohm interpretation, each photon has a definite position and momentum. And you let it run for a while. And after a while, the locations of these photons, each of these little squares, as you see here, form lines. As you see here is the one that goes straight ahead, the E line, and each of these lines then corresponds to one of the directions you see there. Now, let's take a look at this a little closer, and you'll see what the importance of this is. Here's a slice of that, and you'll see here, 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 and here, there are voids forming. In other words, what's happening is the photons are forming into clumps, as you see. And these clumps are going to form something like the de Broglie wave, where you're going to have waves of particles hitting some structure. But that's going to then provide some impetus for the de Broglie. So this is what's happening with a single photon in our simulation. Here I positioned a photon between the screen over here and the mask has a void in it. The waves that come from here are going to go to the screen and reflect back. The waves going to the rearward are going to go to the screen and reflect back, or they're going to go to the void area and continue on going. They won't reflect back. And so all the waves that come back to the photon are then going to direct it. And what it's going to do is direct it in terms of the well-known Fraunhofer type diffraction pattern, which is the same kind of pattern that you get with dipole antenna arrays. If a mask is simulated, a diffraction pattern ends up being on a screen. So we start with photons coming in. And here in the simulation, I'm tracking several photons. They come in, and some of them start to be directed towards the mass. Now, Newton noted this, and so did Young, that they tend to start moving towards the mass before it reaches the mass. The other thing we notice is that in this area and this area, there seems to be an assembly of photons. So these areas appear brighter. And this also has been noted by experimenters who look at diffraction images and masking. The other thing to note here is that photons that come in from the upper part are reflected towards the bottom, and those photons coming in below the center are reflected towards the top. This has been noted by several experiments I've done that it does actually appear to be the way it works. Now, you'll also notice that over on the screen, we're getting peaks, which then are the images we see on the screen. So the simulation is working. On the screen, when we count the number of photons that arrive at particular places on the screen, we'll notice that the intensity then fits very well for a Fraunhofer equation. And you can see the actual counts are these little lines, and the solid line here is the Fraunhofer equation. That if other matter is added, such as a detector, the plenum is changed. That is to say, the waves reflect off that detector and then change the direction of the photon. And this is as quantum mechanics suggests. The suggested simulation then is a very good fit for actual results. And there's the paper that talks about it.
Okay, I think we've come to the end of that video, so we can bring it down. Well, I can probably bring it down, Franklin. Yeah, that's fine. Now, I have checked on the second video, and I think it occupies something over 19 minutes. So I think we might very well have a look at that as well and have a more detailed discussion when we've had the two videos shown. However, we might spend a few moments just reviewing that first video, and in particular, if there are any people in the green room, if there's anybody who wishes to comment on it, just raise his hand. Just a couple of comments myself, maybe preliminary comments. Yeah, I'll just bring you down, Franklin, there just for a moment. John Hodge is up. Yeah. I think John's camera's off, but you probably have no audio, do you, John? Can you speak? No, I think there's very little. We'll just bring John down for a moment. So, well, just a few observations, maybe just to set the ball rolling. John earlier on said, well, the MMX did not show evidence of an ether, but I mean that is perhaps questionable. Maybe it did show some effects. I was also interested where you showed three aspects of what you talked about: mass, weight, inertial mass, and gravitational mass, and yet I would have considered weight to be a manifestation of gravitational mass. So maybe there were two elements instead of three. Let's say I had one or two other comments here. Yeah, I was interested in your proposition that light actually bends before it reaches, say, a diffraction slit. And I'm just wondering how much before might that be the case, and what sort of experiments have been done to indicate that variation? How far back do you have to go not to see any such effect? You also said, sorry, a few observations here. You said that general relativity was not Machian, whereas I would have considered maybe it was, going to the ultimate with regard to the relativity, not only of inertial motion, but of non-inertial motion. And maybe just perhaps lastly, I was interested in your indication of the Biot-Savart law being rejected and so on, and the STOE replacing it. I'm wondering, have you looked at some similar statements, maybe coming from a different angle, made by J.P. Wesley, where he looks at things like, you know, they're not being a B field, but an induction, and he looks at maybe the A field, where B is the curl of A, being fundamental, and he talks about the Biot-Savart not conserving energy and not complying with Newton's third law, and he substitutes the original Ampere law. So I'm just wondering, is the STOE compatible with Ampere's law, or is it a modification thereof? Now, I'm not sure if John is going to be able to address any of those. He's gone from the thing. So there was one comment I noticed. What I think he may have addressed it. It said it's far back, so I'll not get it. But it said he'd be interested in seeing those same experiments done in the southern hemisphere, presumably influenced differently with regard to the north-south magnetic axis of the Earth. However, let's just spend a minute or two more before going on to the second video, just to see, in case anybody wants to come in. So there's Vladimir, there's Bob, there's Franklin, there's Cornelis. I'm not sure if Cornelis is still there. Dennis. Dennis is very welcome back. You're welcome back, Danny, if you'd like to say something. Or James Keane, or James Arathon again. Arathon, actually, I pronounce his name. Yeah, we haven't seen him for some time. You're very welcome back. But you may wish to save your comments until I address you specifically. So, without further ado, let's go on to the second video then, Franklin. If you could maybe the second link we have, I think it takes about. You've got it up. Yes, capital. We're just not getting sound yet. Yeah, I think we have it now. So I'll remove the two of us then.
This video is about a light interference experiment. We're going to show you how to do it. This experiment rejects all wave models of light and all wave particle duality models. The idealism of science is that a valid experiment trumps any model. So here we have an experiment which is repeatable. I'm doing this so that an amateur scientist can do this experiment on his own and see for himself the results. Light interference is at the heart of quantum mechanics. If we have a particle model of light that can produce interference, then we question quantum mechanics.
So this is the experiment. This is just a laser pointer, which is easily available to even amateurs. It's directing its laser beam onto a slit. This is a single slit. It's made out of, here's a business card. We put a hole in the business card and a piece of aluminum foil with a cut in it. The cut is about a 0.5 millimeter wide. And you can see the light coming through the slit. Now this produces a diffraction pattern. And there you see the diffraction pattern projected on a white background, which is about 8 meters away. This is the screen image from the light through the first slit onto the screen, which you saw was 8 meters away. This is a normal diffraction pattern. The laser beam is directed onto a second mask. The second mask consists of glass plates. This is just normal window pane glass. And you see here, the direct diffraction pattern goes through the glass. Now, this part of the experiment is known as the Hodge experiment, which was explored in an earlier video. This is experiment B, where we put a piece of glass between the first slit and the screen. The glass is transmitting the image fairly well. Now we direct the laser beam and this diffraction pattern through a very narrow slit, about a 0.5 millimeter across, between two pieces of glass. You'll see there's the diffraction pattern. This is the third experiment where we put the slit over the center of the diffraction pattern. And you see what you get here, if you can see these little lines here, those are interference fringes in all the various sections of the diffraction pattern. And here's an expanded view of this area in here. We put a nail in the path of the light, and you can see that the center portion of the light here of the diffraction pattern is totally on the nail. That's to say, the first minima are on each side of the nail. That the light from the center portion, that is to say, the light that was going through the slit, is no longer going through the slit, as you can see here. But yet, there's no light going through the slit, but yet the interference pattern remains. And here you see where we put the nail in. The nail is right, this is the shadow of the nail. There's a couple things to notice. One is the diffraction pattern is intact. These are interference fringes, and they are still there when the center of the image is blocked. Another thing I'll note is you see a very faint piece of light right there and right there. And the nail shadow is right in here. So there's no light coming in where the nail is, where the center peak used to be, and we still have interference fringes without light going through the slit. This is the basic Hodge experiment. We had a laser, and we had a single slit screen or mask here, which then let through, and if you remember what this was a regular diffraction pattern that fit the Fraunhofer equation. And then 8 meters away, we had the screen. And of course, that paper. This comes from that paper. This is a computer toy simulation of the image onto the second mask. That is to say, it's the image from the first mask that's projecting onto the glass plates. This is a regular Fraunhofer type diffraction pattern, which is expected by traditional physics. We put the edge of the glass slit right there and right there. So this part goes through the glass slit. Now, you'll note that that is not uniform distribution across the slit. That's part of the Hodge simulation. The other thing you'll note is some of the light here is impinging still on the glass by the side of the slit. I remarked on that. The blocking nail edges are at the minima of the diffraction image. No light through the slit. Now let's see that. This is the edge of a mask, and here we position the edge right in the middle of the diffraction pattern. The image on the screen of this kind of setup is like this. So here you can see the diffraction pattern on that side, but there's the center of the image. This comes through, but more importantly for this experiment, a lot of light comes through behind the mask. Now, traditional physics explains this. But this is what happens when you put the edge of a blocking mask at the minima of a diffraction pattern. What you see here, and it's kind of hard to follow this down, but still there's a very small amount of light that comes right just inside the mask here, and then the rest of the diffraction pattern follows. The point is that where the center peak used to be, there's no light. This is the simulation of the present experiment, and this then is image C that we saw before. So here you see the peak, here you see the secondary maxima and minima. Now, what we're going to look at next is this part of this image, just to show you these little squiggles, what they are. And this is it. This then is the big peak over here. That's the first minima. And then this is that diffraction pattern. But inside the diffraction pattern, there are these zeros here, which represent interference fringes. So you see the simulation is duplicating the interference fringes and therefore the diffraction pattern. Traditional science requires light to pass through slits in order to form the interference pattern. This experiment places the slits one in front of the other, but we still have a diffraction image, and we still have a second slit that is causing the diffraction pattern to go to an interference pattern. The second introduces the interference friction. This is then a double slit experiment, just not what you usually think of as one. Now, the light from the center of the first slit is blocked. And we saw by putting that edge of the slit at the minima, all the light is blocked. There's no light going through the slit. Therefore, the remainder of the first slit diffraction pattern passes through the glass and is coherent. So you can see this video for a discussion on what coherence is. The resulting interference pattern is not formed by the interference of light through the second mask slit. And of course, the light going through the glass isn't changed either. So therefore, the mere presence of a slit must form the interference pattern. Now, traditional science cannot explain this, and wave models of light don't explain this. The STOE model suggests the diffraction images, you can see the reference video, and the interference images are formed by reflecting the plenum waves, which direct the photon's path, just like in general relativity. The lack of a reflecting surface in the gap means the remaining part of the mass directs the photons onto the interface pattern on the screen. Light diffraction and interference is at the heart of quantum mechanics. But here we've rejected the wave part of quantum mechanics.
Here are a few other papers I've written. Note that when a photon pulse is emitted from an atom or absorbed, the electron undergoes a level change and a photon is emitted or absorbed. That's the current model. I interpret this as indicating that photons are part of the structure of the atoms, rather than the electron absorbs or emits the photon. So here then is the atomic structure of the atoms. Here we see electrons being held in place by photons. These go to the nucleus, and these are held next to each other. And of course, those going out are going to other electrons, or they're just free. You'll note that when you take this assembly of electrons and kind of shake it a little bit, what you get is a small little angle right in here. And this angle has two bounds. One, in terms of making a circle of these electrons, produces 8 electrons in a circle, and the other produces 18 electrons in a circle. These are magic numbers in atomic structure. And this is how you form an ionic bond. With the magnetic attractions here, you have a place where an electron might be in the structure, but isn't. And so here's another electron attached to another atom out this way, and you can see that it can fit right in here. You will also note that there's a lot of magnetic force here, and here, and this creates a potential magnetic force here, which the semiconductor folks call a hole. This is how you have hole conduction. You'll note that gravity, that is to say, the gradient of the plenum, has an effect on the surface area of the Hod. But if you remember what a photon looks like, you'll see that a photon only has a surface, just one type of surface, and that force then is directed along the axis of the photon and not in the direction of movement. The direction perpendicular to the plane in the center of the photon has the force equal to 0. The neutrino structure had 2 axes, and therefore the force along one of these axes is, as you see here, not the full force. A three-dimensional body, such an electron, has the force being able to be produced in 3 different directions, and therefore it is a smaller force than is on Hodge. So there's different types of forces, and this produces some interesting phenomenon. Note an interesting thing about magnets. If you have a north-south magnet, another magnet is going to be attracted either slightly to the left or slightly to the right. These are little balls, and what we're doing is proposing, following Emmanuel's, who I mentioned earlier, suggestion that nucleons, that is to say protons and neutrons, are spheres of balls of magnets. And each of these magnets on the surface has its axial magnetic force tangent to the ball. So therefore, the magnetic attraction is inverse cubed radially. And of course, it attracts all other magnets, either north or south. And this then is what the STOE proposes, is the strong and weak nuclear forces. That is to say, we now have all the gut forces, strong and weak nuclear forces, gravity, and the magnetic and electric forces. This then is what a nucleus might look like. Several balls like this all lined up. Now, the interesting thing about this structure is that if you have a ball, these 2 balls of magnets like that, there's an extra force here at the opposite end of where this is that attracts photons. And you'll see that if there's other photons coming out from here, such as here, they are directed back to be in more or less the actual direction of the structure. And this kind of a structure, where it goes in a loop, isn't allowed, it's prohibited. So here you have a single photon structure that ends up being the attachment to an electron. 1 electron per 1 proton. The STOE has made several predictions that we have covered. The interference of light in the transparent mass experiment was actually predicted, meaning I was looking for that kind of a thing. I had tried several other experiments trying to show the model worked, and there was someone who I was in communication with at the time, a Dr. Sato, and he was always able to come up with an additional assumption that you could make to the wave model that would fit my experiments. But that really led to not only Fraunhofer's 5 weird assumptions, but many more types of assumptions. Well, I guess that's what physics do. But in this transparent mask experiment, that's when Dr. Sato quit trying to figure out how it worked. The Hodge apparatus, which is a laser with a single slit, produces a diffraction pattern with a very well-known distribution, that is, say, the Fraunhofer distribution. Now, one of the problems you might run into if you're going to do these experiments is pen lasers, and I've looked at several, produce slightly different types of dots. That is to say, they have optics in them that produce these dots, and these dots may have a structure. The difficulty with this is it's really kind of an unknown structure, and it produces some weird effects sometimes, especially if you're going to use very narrow slits. Very narrow slits will do what's called resolve the image. So this is some experimental issue that you kind of have to watch out for. The maybe, I started noticing the Maxwell's equations differ from the STOE. The experiment rejected the Biot-Savart law was done because the EM radio signals travel at the speed of light, which implies odds are the elements. However, this seemed to conflict with the Biot-Savart law. So the typical experiment was done using a magnet rather than a parallel wire. The result of the experiment suggested in the STOE another experiment on electromagnetics, which showed two different types of magnetic field, and that Maxwell's equation should be redone. Well, I guess we're near the end of the time here. And the STOE model also looked at cosmology models, but perhaps that could be an issue for another time.
Very well. Thank you very much indeed. Now, I've been monitoring some of the comments coming in, and in particular, John has agreed to answer any questions, either coming directly into the comments or made by people in the green room, whom I may invite in a moment. He's offered to answer those questions in the chat. This is the general comments. So with your forbearance, I think we'll have to operate that way because his system is quite down. It's impossible. So just perusing some of the answers there, he's addressed somewhat the question of the Biot-Savart law, which I want to delve into a bit deeper. I'm not quite sure if John, you're familiar with Wesley's work. You say the STOE is at variance with Ampere's original force law, which surprised me a little, but I'm just wondering, are you familiar with J.P. Wesley's work, and have you compared his conclusions with your own? So you may wish to add that. Okay. A lot of these points here are comments. So unless you have any very specific questions in the general chat, I'll endeavor to see other people in the green room who'd like to come in because time is pressing on us. Is there anybody who would like to make some observations on this whole question of the scalar theory of everything? And James Keane has put his hand up. I'm bringing you up now. You're up, Jim. So please.
Well, I'd like to thank John Hodge for a very interesting presentation. I have one basic question, which maybe indicates I don't understand something, or at least, well, let's see. The question is, in the nail experiment where you're blocking the light, the center of the laser pulse, are you saying that the light corpuscles are not necessarily traveling in a straight line, since the nail is blocking it, to produce the interference pattern which you observe even though the nail is blocking the center. Is that clear, that question? I hope so.
So well, it's sort of clear to me, but I'm assuming that John has got that, and that he'll be able to type in some sort of response. It's not a very satisfactory.
It's either straight line or some curved path or other path other than being a straight line. If it's not necessarily only a straight line path, that would be consistent with my work as well. So I'll sign off. That was my question. And
I'm saying no light through the slit. That's what he says in the comment. And I'm wondering if this is not unrelated to the...
But I thought there was an interference pattern, even though the center was blank.
Yeah, well, he says that this diffraction occurs before it reaches the slit or the nail, I dare say. But then he comes back, he says, but interference still occurs. So...
So light must not be going in a straight line. Are there other paths possible?
Yeah, he hasn't actually addressed that. He just says it goes through the slit. Would you like to address whether you think it's dead straight or is it curved, the light path, John? Because we're getting other comments in, like up and down around atoms or clusters of atoms and so on. So how do we have light with no light?
Well, I'd be interested in the answer to that. And
okay,
that was my only question at the moment, sir.
Thank you very much, Jim. No also light in straight line. But of course, Jim, you have access to the general comments as well as the private chat. So you can see if John wishes to post something a bit more detailed in the next 5 minutes or something, you can see it.
Thank you, sir.
Okay, thank you very much for your comments. I'll see. Is there anything else now? Okay, very good. Now, it's my tendency actually to bring almost everybody in from the green room, whether he volunteers or not. John has said something else. So STOE suggests plenum waves from photons go back to sense slits. Yeah. Okay. Well, Vladimir, could I impose upon you just to give any response at all, brief or a question? I'd value your input at this stage.
You know what? Thank you so much for invitation. I want to tell you that today I expected to hear something about Scalar Theory of Everything. And unfortunately, I didn't get their opinion about this theory because it's the most important part of this presentation, it seemed to me. The second point, you know my opinion about the mixture of classical physics and quantum physics. It's two different stories, two different, physics. That's why right now we listen to the theory of mixture between quantum objects and classical physics. And the next very interesting question I want to ask John, how he can explain such a very interesting experiment. You have your interferometer Michelson. You are looking for interference pattern. It's standard, everybody knows, and so on and so on. If in one shoulder you will put some plate window and you will reflect a part of this radiation to some photo element, and you will start to watch your photons going to photo element, and it's a miracle. You will not see this interference pattern at all. This is a very interesting experiment, and it's a well-known picture. That's why interference a diffraction. It's not so easy as it seemed 100 years ago, 200 years ago. Now with all our techniques, we can watch some unique experiments. As I told you, you're watching your beams, immediately you lost your interference pattern. You're not watching, it's free, then you can see standard pattern. It's a very interesting question, how to explain it. I would like to ask him to explain it, but I don't know how to do it.
Right. Somebody is agreeing with you in some respect anyway. But unfortunately, owing to the difficulties we're having, the only way for John to respond to that, Vladimir, would be to put some comments in here. Well, it's true. For my own part, I might just suggest that a theory of everything is a very ambitious statement. But of course, the mainstream are using it. They're all, Hawking and they're all saying we're going for this. I suppose Einstein as well earlier on. So maybe by its nature, it's unlikely to deliver what it claims to. But it was quite an ambitious title for today's lecture.
Yes, it's exactly my point, man. I expected to hear, because it's the most interesting part of it. All these experiments with interference, diffraction, it's very interesting. I'm an optical guy. I worked for lasers for the whole life. I'm a laser physicist. That's why I know something about lights, about all these effects. But, the main goal of me was to hear about theory of everything, not about the experiments. Experiments is fine. And my opinion that we must not use classical notions like field, electromagnetic field, magnetic, and all this stuff in quantum objects. It's two different stories. We have classical physics with Michelson. Okay.
Is that true?
Why we cannot transfer our knowledge from classical physics to quantum physics, and I'm absolutely sure with this.
Okay, he's come back with a couple of comments. Plenum waves reflect off any objects which destroys interference. So he says, and he also says STOE is particle and wave interference. Particle and wave interference.
I don't know how to interfere particles and waves. I don't know. I'm a laser physicist, but I cannot even imagine it. I'm sorry.
Right.
Particle is particle. Quantum objects, they have only 4 momenta. That's it. Energy, pulse, and that's it. That's it. And waves, it's a classical notion. And waves, it's an ensemble of photons. It is a totally different story. It's like, some stream of photons.
He says this, and actually in the, I'm not sure if it was in the blurb or in his emails to me, his private emails, he did say something of this nature. He said that TOE is one model for all size scales. So I think to a certain extent, if I may speak for John, that's partly what he meant by everything. He means that the one model can be applied to the microscopic, the intermediate, and the macroscopic. Now, I'm not sure if that's totally satisfactory.
I'm sorry, but it is written that it's united 4 forces, extended Newton theory. It's so.
STOA is particles emit waves in plenum, which then directs particles, just like GR suggests. Yeah, it's very hard to get full answers by these telegraphic messages, and I'm not blaming the system, but TOE, the marriage of micro and macro, that's part of it. It's not. I agree with you that it is more. It's meant to integrate the 4 forces, and we might need to get more information on that. Maybe another talk at some stage.
So by the way, let me tell you about forces. In electromagnetic theory, in Maxwell equations, we don't have forces at all. We have only energy density, charge density. We have a flow of density, and that's it. There are no particles. There are no forces. Forces, we invented this, No.
Well, you can define those, related to a potential gradient or something like that per unit charge or mass.
But it's already we invented. We have our inertial mass as a coefficient. That's it. We are measuring something. I don't know.
They're conventions, maybe to a certain extent. That's true.
Yeah.
You know how we express these.
And gravitation and mass and inertial mass, it's a totally different stories. Later, when in one of my presentation, I will show the difference, what is going on with it one, and why the difference is between quantum physics and classical physics. It's very difficult for me to take this mixture and trying to explain in one equations, in one theory, all these, from my microscopic to microscopic to cosmological, parameters to cosmological, objects. I cannot even imagine it, how it can be done.
Okay, well, don't steal your own thunder. We're all looking forward to your presentations next month.
I'll do it with my pleasure.
Thanks very much, and please keep an eye on the comments because he may be coming back with more enlightenment on that. So thanks very much, Vladimir, for those comments.
My pleasure.
Yeah, I'm still interested in exactly how the STOE would conflict with the Ampere force law. I'm interested maybe almost mathematically in having an equation to show you where the disparity is. So that might be something. Okay, now I'm going through these things sequentially. Anybody else want to come in immediately? Well, Franklin, who's been helping me with co-hosting, have you any technical issues you'd like to, bring to our attention at least, Franklin?
Well, I just I was reviewing the video. What's interesting here is that John has some very hands-on experiments. So I certainly like that. And so I was reviewing one of the experiments here. So maybe we can go back to reviewing that.
Is that the comment there?
Yeah. So, we have, for example, this experiment here where he's trying to show that, say, the north sides repel more than the south sides. So, it looks like we have an experiment here. So he's got the black magnets facing each other, and he's put white strips to indicate, where they're positioned. Okay, so that was clear. But and then he reverses it so that the red sides are facing each other. So he does like a quick video slice here. Okay, so now to me it looks like where the white papers are showing where the distance is. That looks pretty much the same to me. Is that what it looks like to you, Ian? So it's because I would be very surprised if this were true, that say the north sides repelled less than the south sides. And, he says that the difference is like one magnet's worth, but it looks the same to me. So that's certainly one interesting experiment. Let's see, let's look at his other experiments here. So, but he is saying that, the difference is gravity, I guess. So but if you can't really demonstrate that, then that would not be a good point. So, but the second experiment here, so, the interesting thing here is that when he puts the wire completely off the magnet, so that the current is only flowing in, beside the magnet, that doesn't seem to have any effect. Now that's kind of interesting because I would not have expected that to be the case. And, he's making the point that whatever the magnetic field is coming off only tangentially. Although I don't know whether that's true or whether that's just because the magnetic field is so weak and falls off so rapidly that the current, which is coming, from the left side of the magnet here, is just too weak to affect this. But, it's an interesting observation there. And let's see here. So then we have the Ampere law test here. So I'm not familiar enough with Ampere's law to know whether there should be a difference, whether the magnet is being dropped straight through the center or through the edge. So Ian, I'm not sure whether you're familiar with that, whether you would have expected a difference there.
Yeah, I'm not quite certain about that. There possibly could have been a small difference, but I'm just interested in the basic contradiction that if I'm not using too strong a word, that John says exists between the Ampere force law and the STOE force law. I'd like to see maybe some equation of that nature, Franklin.
Yeah, I'm not sure. I didn't really catch the whole Ampere's law thing. I mean, the things that I am getting from the theory, he very much favors, say, the particle theory of light, and his second video was I think all about proving that. That was the introduction, and but I wasn't terribly convinced because the only experiments you can use are, of course, with, say, light. And so any experiment you can use with light is not going to be able to tell you what its actual nature is. And so the other thing is that he's using a glass slit. And I don't know what the significance is of using, say, glass to make a slit. All other slit experiments I've ever seen use, of course, a solid slit, and I'm not an
opaque medium slit.
Yes, opaque. So I'm not sure what the significance was of using the glass. And now my bias is that say is the opposite, which is light is a wave. So I would argue that I wouldn't know, even as a wave proponent, would know what to expect if you put light through a glass slit, right? I mean, it could do practically anything. So, he has his results, but as a wave proponent, I would not be convinced by his conclusions, because I can't really see where, I guess he must have some precise calculations and such. He had the predictions and things like that.
Okay, well, John may wish to, where he's put something in, Franklin. The experiment rejects wave models. Actually, it's even stronger than you said. You said he veered towards the particle model.
Yeah, no, I don't think the experiment rejects waves model, at least from what I could see. I can't analyze. I don't have, his computer simulations or whatnot. But, just given the pictures, I would say, yeah, sure, waves do that. They can do that. I mean, I don't see why they wouldn't travel behind the nail or create these other little things that he was pointing out. None of that is incompatible with the light nature, the light being a wave nature. But like I said, I don't know why, a glass would make a difference. I'm just saying that nothing that he showed there seemed at all incompatible with the light model of light.
Right, that's well taken. Somebody's asking you a question. Would you yourself say that you accept the concept of photons? This was a general question.
Well, my own personal opinion is that what we're seeing with light, particularly visible light or light produced by atomic action, comes in, I would say, a packet. I would say light is strictly a wave, that there's a medium and that light is a wave through that medium. But what we see, but it has these particle properties, like some people are asking, Can you find, say, and isolate an individual photon? And experimentalists, have. So, for example, when you collide a positron with an electron, it generates like exactly 2 gamma rays going in opposite directions. And those actually are individual photons. But what those gamma rays are, I feel, are just very short wave packets. So it's just like if you take a rope and you just hit it once and it sends a wave, and that wave is just a bump in the rope that just travels down as a single thing. But it's not like a single wave. Well, it could potentially be a single wave. People call those like phonons. But my analogy is that the light is generated somewhat like this pencil here. So it has a start, it has an end, it moves through space, it acts like an arrow through space. So every single photon, actually, because it's generated by atomic processes, has actually the same energy. The only difference is for example, how long this pencil would be, for example, the only difference between a high frequency photon and a low frequency photon. But that's how I try and reconcile this whole wave particle duality, right? So me personally, I don't like to have theories which have to kind of bootstrap themselves, right? So I don't like saying like particles are made out of waves, because if you have a wave, then there has to be a medium, and those mediums have to be made out of particles. So I don't consider that a good starting point. I prefer to start with a particle, say electrons or whatever, something that we know about, fill the entire space with those things, and then you can have waves through that medium. But you do have to explain this. What's going on? Why do we see these interference patterns? Because another point is that I think people have been able to show that interference patterns does happen with particles. Like I think there's an experiment where they use, say, these buckyballs, which is one of the very largest molecular molecules you can have. And, they shoot those through slits, and indeed they show, say, interference patterns, And my feeling is that, yeah, you could probably do that with basketballs, really, through a gym hall. If you threw enough basketballs through there, perhaps you might see the same interference patterns.
Okay, Franklin, thank you very much for those comments. I have a few things coming in related to what you're saying, actually, there. A question from Nick and so on. So maybe, with your permission, I'll address those now and move on. So thanks very much, Franklin. You see, Nick Purcell asks, John, are you saying that a photon is a particle, but it acquires wave characteristics by its interaction with the plenum? And then John has answered that. Photon causes waves in the plenum. Alan Kelly here said his conclusion, with the help of Oxbridge professor, is that you can't speak about a photon once the energy has left the emitting media. I don't know, this is probably a convention or something. Cornelis has asked a question. The medium is in a bond medium, not discrete particle medium. The bond is fundamental in all cases at all levels. Yes, electrons are particles which cause waves in the plenum. Well, at least we're homing in a little on that. So let me see, can I just erase that screen? So Cornelis, if you could just maybe expand a little, as briefly as possible, because we are running out of time.
Well, I like John's theory from the standpoint of a couple of things. He uses Mach's principle, where things
out there are affecting inertial and gravity characteristics. Basically, on the bond medium thing is his all the interactions that occur within his theory occur because of wave interactions through the plenum. I think that's basically, he has a focal point, but his focal point is basically a magnet, which I feel is much more complex than just it excel. I don't know if he's been able to explain himself where magnetism comes from. It just magnetism was assumed in the last talk he had in 2021 with the group. And so that was basically a fundamental. The Hodge was a fundamental thing that just existed with the magnetic probability or characteristics. The plenum is the main thing that carries all the energy and the distortions of the plenum. Basically, gradients in the plenum are what basically directs all motion. It just carries it one step farther, where the plenum itself can become so deformed that it appears as a particle. So that's where, if the plenum is like I said, it's like a bond media, no matter where you go, there is going to be a bond between points in the medium. And the medium itself is just a bond medium. It's continuous, as the plenum well describes, and as John describes it. There's no discreteness to it. So I'm, fully in agreement with that part of his theory. It's just I don't think he needs to go as far as saying that there are magnetic points, that those can be actually just focal points of the plenum itself, and magnetism can be derived from deformations and certain wave characteristics within the plenum. So it's more the design. So that's kind of what I see. I like the idea that he's working with the plenum, and it does explain, the gravitational characteristics, and that I do see photons as a wave.
So if John wants to add anything to the latter part of Cornelis's contribution there, he could put it in the comment, and we'll both view that. So thank you very much, Cornelis, for that comment. Now I'm going through. I'd like to get a word from everybody. I don't know if Dennis Allen, Dr. Dennis Allen, is there. He seems to be there, but his camera is not on. It was on earlier. Are you there, Denny?
Yes.
Yeah, we're very glad to see you.
Thank you.
Have you any observations, any brief observations, or even question for John about today's presentation? Did it deliver what you expected? You're mute, actually, and your camera is off at the moment. Yeah, I got both now.
I didn't know what to expect. The word scalar threw me off. He does apparently use vectors. He talked about 1 over r squared as opposed to, and also 1 over r fields. I think from a public relations point of view, he might have better have used a different name for his theory.
Yeah, it seems to be limiting in a way, at least in somebody's conception, having read it.
And as you pointed out, his magnetic theory doesn't go back to the A field, which is according to the famous experiment. What is it? Cooper-Monstein.
Yes.
The A field is the right field to look at, not the B field. Although you can get quite a ways along with the B field, but the really correct way to look at it is the A field.
Yeah, he seemed to be getting there or moving in that direction, but he hasn't actually answered whether he's familiar with any of that work, Denny.
Yeah, well, Wesley is not everyone's cup of tea.
Right.
When you wrote the book, Scientific Physics, in 2002, he was already quite old, and he didn't have Marquardt to make sure all the words were spelled right and the exponents were right and so on.
Yeah, the second book is a bit easier with Mark.
Yeah, with Marquardt.
Okay.
And but I think he's done a lot of good work. His photon theory, it's a little bit hard for me to believe, although it does seem to correspond with experiment quite a bit. He's not just a pie in the sky theorist. He makes sure his theory is in touch with reality. But the columns, I don't know if I can. I don't know if I can believe that or not. Although if you use that model, you get the right answer. It's hard to criticize it.
So I'm not sure if I quite got that. What aspect of it did you say? The columns or something?
Yeah, it is photons or columns, he said.
Oh, yes, okay.
And whereas Wesley talked about the positron electron photon, which he, however, could not make go because he messed up on his he got the what's the word not the well, you know what I mean. We long had a discussion about whether or not there should be a factor of 2 or 1.
Right.
Now, what is the proper terminology just for people who are listening?
Well, did you mean like whether we were duplicating or not, whether we were counting twice?
Yeah. But what were we talking about? What were those equations about? Well, what's the proper term?
They were more about the generalized Poynting vector and energy density.
Energy density, that's it. Yeah.
Okay.
Here, John has
the columns is to give the Fraunhofer equation when it moves.
Yeah, well, if it does give the right answer, even though it's hard to believe, it might be very useful.
Right. Yeah. It's a bit like these models of atomic nuclear reactions.
Yeah, one model has electrons orbiting the nucleus, and whereas Bill Lucas and his son, one of his sons, have a model where the things don't orbit, they just vibrate.
Yes.
And he seems to get very good results. I'm impressed by John's work.
By their fruits ye shall know them, perhaps, yes.
Yeah.
Well, thank you very much for those comments. And again, we'll keep an eye on the responses. John may have more specific responses. Great to have you back, and hope to see you again in the continuing future.
Well, I'm still not well, but they told me I was in stage 4 of cancer and had 6 months to a year to live. But I'm using holistic methods, and it seems to be working.
Well, that's very good, because the initial email seemed to be dire, just negative and so on. So I hope there is some positivity. Don't take all the physicians' gloom and doom. There's always light at the end of the tunnel.
The holistic methods have been because you can't patent something that's a natural substance by law. Any natural substance can't really be advertised as being helpful because the federal government comes down and says, well, you haven't shown us by, statistically correct methods, placebos and, it's, I can't.
They have a vested interest in putting it down, probably.
Yeah, because, if it put radiation and chemo out of business, that's a huge cash cow. Huge.
Right.
And so, but the people who are selling natural substances can't jump through all these hoops, placebo, double blind, all this. It costs a huge amount of money. And since they can't patent the natural substance, they can't possibly afford to do that. So when they insist on these statistically super correct methods, they're in effect outlawing all holistic methods.
Yeah, well, thank you. I mean, this brief conversation, one might say, is a bit off topic, but actually, it's very relevant to the whole concept of what our organization is about and what our sessions are about. Critical thinking, just saying that because it's laid down by the high priests of science or medicine or whatever, it cannot be questioned. We question all that, and for my own part, I would say that there's nothing to be lost by using natural means. There may be benefits there too. There could be great losses to using artificial, very concentrated medicines with all the side effects. So do by all means continue, and we'll talk to you again in the near future about that. So
thank you.
Thank you very much. Good to see you again, Denny.
Thanks very much.
And thank you for your comments as well. So just before, the time has really caught up with us, but James Arathon has sent me a message to say that he'd be able to attend today. I don't know if you're there. You're muted, James, and also you are there. You came back. So
all right, yeah.
I'm sorry, but I just give you an opportunity very, very briefly, because we're running out of time now, just to say anything. Either just a response to today's talk, or maybe what we might do in the future. Or
sorry, I just make a quick comment in the relation to the mainstream thought and critical thought, because in the mainstream thought, every theory has its own space. So in Newton's gravity, there's a action at a distance. There is a sort of no way of connecting two objects. They just have some force on each other. In electromagnetism, there's some sort of field, but it's a pseudo field, and there's a vector field in mathematics to describe the interactions. And then in every physical theory you can name, there's a different way of describing what's happening in the space. And I think that would be my criticism of John Hodge's theory. You've got to explain exactly what's happening in space to improve on the mainstream thought, because every domain has its own little way of describing what's happening in the space between two objects, and to make progress, we've got to understand what it is holistically is happening with the similar mathematics. That's my real comment. To summarize which is too much of a criticism, really, because hundreds of years of mainstream science hasn't solved this problem. So yeah.
What has John said here? Franklin, to you, I'd like the following on your take of the experiments. Yeah. Okay. Well, look, the main thing is all comments, including critical comments, because that's what we're all about, and we don't have sort of we have a couple of mainstream people who are always giving very strong comments, which we welcome, maybe against a lot of our concepts. So I think John can only but benefit from comments such as the ones you've made, James, and give further possibilities for looking into. I would agree with the person speaking. Yeah. Okay. So thank you very much, James. Just before I leave you, we're expecting a further contribution from you at some stage. It's been some time, so you may wait.
Well, I've now made much progress on dimensional analysis, and I think I can, because the SI system was based on Giorgi's original.
Yes. Yes.
And I think it can be done a bit further and maybe think about mass in a new way. So I think from a dimensional analysis point of view, that doesn't solve everything, but just thinking about measurements and how they all go together and in a sort of dimensional analysis framework. Yeah, that's progress.
And is there any progress on the O'Reilly research?
No, I'm going to visit Ireland in the summer, so I'll contact you.
Well, you'll have to
that.
get in touch with me. You'll have to. So do keep in touch and send me an email if you're ready to do anything on the dimensional analysis or the other, or what your plans are, and I can fit you in. You know, we're sort of we're running out of people come April. I think we're all right for the moment, but you know, so I'd be able to fit you in anytime.
Yeah.
So thanks very much for coming, and hope to see you again, James.
Okay, cheers. Bye.
Bye now. Okay, time has caught up with us, everybody, and therefore it is my duty to thank you all very much for your contributions. Thank everybody in the social media, the Facebook and the YouTube, and everybody in the green room whom I did twist everybody's arms to come in and make contributions, but I think they were all very valuable, and I hope John thinks so as well. He thinks that we've made some pertinent comments. But of course, most of all, I'd like to thank John for taking considerable trouble to give us this talk. Those videos were actually quite illuminating, and I'm sorry that technical problems, which were evidencing themselves in the last weeks, because I was, contacting John about this, and we were looking at it. We thought we might be able to resolve it today, but unfortunately we didn't. But the next best thing was to have John here available, putting comments in, listening with open ears to what everybody has to say. I know we've learned a lot actually from his ideas. Now, some perhaps it promised. Theory of Everything promises a lot, and whether one can fulfill all the expectations is a moot question. But certainly I found it quite stimulating, and I hope if John actually gained even 1% of what I'm sure all of us have gained from listening to him today, if he's gained that and it prompts him to do some further work in this area based on the feedback, I'll be more than happy. So once again, thank you very much, John, and everybody for participating. I must end the procedures now, and just keep an eye on the notices. We'll be coming back. I'll be coming back in a fortnight's time with something a bit different, and there'll be intermediate ones, probably hosted by Roger and Franklin. So keep an eye on the notices. And thank you again, everybody, and John. Good day.